Welcome to this session where we dive into the problem number 456, 132 pattern. In this challenge, we explore an interesting array-based problem that tests our ability to detect specific patterns efficiently. Let's get started and break it down step by step. The 132 pattern is a specific sequence of three integers within an array. For a sequence to be considered a 132 pattern, we need three indices, I, j, and k, such that I comes before j, and j comes before k. Additionally, the values at these indices must meet a specific condition. The value at a_k must lie between a_I and a_j. In simpler terms, a_I is the smallest, a_j is the largest, and a_k sits between them. Your task for this problem is to determine if such a pattern exists within the input array. The input is an array of integers, nums, and you'll return true if at least one valid 132 pattern exists, or false if no such pattern is found. Let's look at a few examples to clarify this further. In the first example, the input array is 1, 2, 3, 4. The output is false, and here's why: the numbers in the array are strictly increasing, which means no valid triplet exists that satisfies the 132 pattern condition. There's no middle value that lies between a smaller and a larger number. So, for this array, the result is false. Now, consider the second example with the input 3, 1, 4, 2. This time, the output is true because a valid 132 pattern can be found. Let's break this down further. In the second example, the triplet 1, 4, 2 forms a valid 132 pattern. Here, 1 is the smallest value, which corresponds to a_I. Then, 4 is the largest value in the triplet, making it a_j. Finally, 2 lies between 1 and 4, which makes it a_k. Together, these values satisfy the condition for a 132 pattern. This shows that the array does indeed contain a valid sequence. In the third example, the input is -1, 3, 2, 0. Again, the output is true, as there is at least one valid 132 pattern. Let's explore that in more detail. In the third example, the triplet 2, 3, 0 forms a valid 132 pattern. Here, 2 is the smallest value in the triplet, which makes it a_I. The number 3 is the largest value, so it represents a_j. Finally, 0 lies between 2 and 3, making it a_k. Additionally, the array contains other valid triplets, such as -1, 3, 0. These variations further illustrate how 132 patterns can emerge in different ways within the same array. Now let's consider the constraints and edge cases that you need to handle while solving this problem. The constraints specify that the input array has a length of n, where n can range from 1 to 10,000. The values within the array can be as small as -10⁻9 or as large as 10⁻9. Some important edge cases to consider include arrays with fewer than 3 elements, such as 1 or 1, 2. These should return false because no triplet can be formed. Similarly, arrays with all elements equal, like 1, 1, 1, cannot produce a valid 132 pattern and should also return false. Finally, arrays with negative numbers or zeros, such as -1, 0, -2, -3, need careful handling to ensure valid patterns are identified correctly. With these considerations in mind, it's critical to aim for an optimized solution, as brute force approaches may not be efficient enough for larger inputs. To start, the brute force approach is the most intuitive way to solve the 132 pattern problem. It involves checking all possible triplets in the array, ensuring that the indices satisfy the condition I less than j less than k and the values meet a, k, j. This can be achieved using 3 nested loops, where each loop corresponds to one of the indices. While this approach is straightforward and easy to understand, it has a significant drawback: its time complexity is cubic, n cubed, because it iterates through all possible combinations of 3 indices. Additionally, it has constant space complexity, 1, as it does not require any additional data structures. However, the computational cost becomes prohibitive for large input sizes, such as when the array contains tens of thousands of elements. As a result, this method is not practical for solving the problem efficiently. An optimized approach involves leveraging prefix minimums to improve performance. In this strategy, we pre-compute the smallest element to the left of each index, which we call min I. Then, we iterate through the array to identify potential a, k, and a, j values. For each a, j, the goal is to find an a, k to the right of j such that it satisfies the condition min I, a, k, a, j. To efficiently locate a, k, we can use a balanced search tree or a similar sorted data structure. This allows us to perform the necessary comparisons in logarithmic time for each element. While this approach improves the time complexity to O n log n, and uses O n space for storing prefix minimums and the auxiliary structure, it is still somewhat complex to implement. Moreover, the logarithmic search overhead may still be a limiting factor for extremely large datasets. Therefore, although this method is an improvement over brute force, it is not the most efficient or practical solution. The most efficient solution employs a stack-based approach, which uses a monotonic decreasing stack to track potential a, k values. This approach takes advantage of key insights about the problem. Specifically, for a, k to fit between a, I, and a, j, it must be the largest value smaller than a, j, among elements to the right of j. By iterating through the array in reverse, we maintain a stack where elements are stored in decreasing order. This ensures that the top of the stack always represents the smallest valid candidate for a, k. During the iteration, we initialize a variable, third, to track the largest valid a, k, encountered so far. If we find an element nums I that is smaller than third, we know a valid 132 pattern exists, with nums I, third, and some a, j, forming the pattern. To maintain the stack's properties, we pop elements smaller than the current number and update third accordingly. Each element is pushed and popped from the stack at most once, making the time complexity O n, and the space complexity is also O n, due to the stack. The stack-based approach is chosen because it balances efficiency and simplicity, making it an ideal solution for the 132 pattern problem. With linear time complexity, it is well suited for handling large input sizes and avoids the computational overhead of more complex data structures like search trees. By iterating in reverse and leveraging the properties of a monotonic stack, we can efficiently track valid a, k values without needing to explicitly check all possible triplets. This method is not only faster but also easier to implement compared to the prefix minimums approach. While the latter offers theoretical improvements over brute force, its added complexity makes it less appealing in practice. The stack-based strategy is elegant, highly performant, and practical for competitive programming and real-world applications, which is why it is the optimal choice for solving this problem. The 132 pattern problem requires us to find three indices in an array such that the values at these indices form a specific order. Specifically, the value at the first index must be smaller than the value at the third index, which in turn must be smaller than the value at the second index. This pattern is particularly useful in applications like identifying specific trends in stock prices or validating sequences in data. However, solving this problem efficiently is challenging due to its constraints. A straightforward way to solve it is using a brute force approach. In this method, we look at all possible triplets in the array by iterating through the indices with three nested loops. For each triplet, we check if the values satisfy the required condition and return true if we find one. If no such triplet exists after checking all possibilities, we return false. While this is simple to implement, it's computationally expensive because of the need to test every combination, making it impractical for large inputs. To better understand the brute force approach, let's look at its pseudocode. We use three nested loops. The outer loop iterates over each possible starting index, the middle loop explores possible middle indices, and the innermost loop checks for a valid third index. For each combination of indices, we check if the values satisfy the condition a, k, a, j. If we find such a triplet, we immediately return true. If all combinations are exhausted without finding one, we return false. This approach, though correct, has a time complexity of O n cubed, due to the three nested loops, meaning it becomes extremely slow for large arrays. The space complexity, however, is O(1), because no additional storage is used. The inefficiency of this approach highlights the need for optimization. By leveraging the structure of the 132 pattern, where the third element must fit between the first and second, we can develop a more efficient solution. This insight lays the groundwork for reducing the complexity of the algorithm. To address the inefficiencies of the brute force approach, we can use a stack-based algorithm combined with reverse traversal. This optimized method avoids explicitly checking all triplets. Instead, it focuses on maintaining relationships between potential elements of the 132 pattern. First, we initialize an empty stack to hold candidates for the middle value of the pattern, and a variable called third that tracks the maximum valid value for the third element. By traversing the array from the end to the beginning, we ensure that we process potential middle and third elements before considering the smallest. During the traversal, if the current element is smaller than third, we found a valid pattern and return true. Otherwise, while the top of the stack is smaller than the current element, we update third by popping the stack. This ensures third always holds the largest value smaller than the middle element. Finally, we push the current element onto the stack as a new candidate for the middle value. If no valid pattern is found by the end of the traversal, we return false. Here's the pseudocode for the optimized approach. We begin by initializing an empty stack and setting the third variable to -infinity. Then, we traverse the array in reverse. For each element, if it's smaller than third, we immediately return true, as it satisfies the 132 pattern. Otherwise, we process the stack. While the stack isn't empty and the top of the stack is less than the current element, we pop the stack and update third to the popped value. This ensures that third represents the largest valid candidate for the third element of the pattern. After processing the stack, we push the current element onto it as a new candidate for the middle value. If the entire array is traversed without finding a valid pattern, we return false. The stack in this algorithm is crucial for efficiently managing potential middle elements, while the third variable helps track the largest valid value for the third element. This combination allows us to evaluate the 132 pattern in linear time. The optimized solution significantly improves the performance of the algorithm. Its time complexity is O(n), because each element is pushed and popped from the stack at most once. The space complexity is O(n), due to the stack, which stores potential middle elements. Key optimizations include the reverse traversal, which ensures that we process potential third values before considering smaller elements, and the use of the stack, which allows efficient tracking of valid middle values. Additionally, the algorithm terminates early as soon as a valid pattern is detected, saving unnecessary computations. Handling edge cases is also crucial. For example, in an empty array or one with fewer than 3 elements, no pattern can exist, so we return false. Similarly, arrays with all equal values or in strict descending order cannot form a valid 132 pattern. The optimized approach handles large arrays efficiently, making it suitable for real-world scenarios where input sizes can be substantial. This implementation solves the 132 pattern problem efficiently using a stack-based approach. The function find132 pattern takes a list of integers nums and returns a boolean indicating whether the 132 pattern exists. The edge case of fewer than 3 elements is handled at the start, as no such pattern can exist in smaller arrays. Next, a stack is initialized, and a variable third is used to track the 2 in the 132 pattern. This variable is initially set to -infinity, representing no valid 2 found yet. The algorithm iterates over the array in reverse order. This is because we attempt to find the 3 first and work backward to validate the 2 and 1. For each number, if it is smaller than third, it means we've successfully identified a valid 132 pattern. Number is the 1, third is the 2, and a previous stack value was the 3. In this case, the function immediately returns true. If no such pattern is found, the stack is updated. Any numbers smaller than the current number are popped off the stack, and the largest of these becomes the new third. This ensures that third always holds the maximum possible value for the 2 in the 132 pattern without violating the ordering. Finally, the current number is pushed onto the stack to be considered for future iterations. If the loop completes without returning true, the function concludes that number 132 pattern exists and returns false. This approach ensures an efficient runtime of O(n), as each element is pushed and popped from the stack at most once. Here, we're implementing the solution for the 132 pattern problem in Java. The first step involves checking if the length of the input array is less than 3, because a valid 132 pattern requires at least 3 elements. If the condition is true, we return false immediately. Next, we initialize a stack, which will help us keep track of potential 3 values in the 132 pattern as we traverse the array. We also declare a variable named third, initialized to the smallest possible integer value. This variable represents the 2 in the 132 pattern and will be updated dynamically as we process the array. The traversal begins from the end of the array, moving in reverse order. At each step, we check if the current number can serve as the 1 in the 132 pattern, meaning it must be less than the third value. If we find such a number, we immediately return true, as it confirms the existence of the pattern. If not, we proceed to update the third value by popping elements from the stack as long as the top of the stack is smaller than the current number. This ensures that third always holds the largest possible value that could serve as the 2 in the pattern. Finally, we push the current number onto the stack to maintain potential candidates for the 3 value. After completing the reverse traversal of the array, if no valid 132 pattern is found, we simply return false. This indicates that no combination of 3 numbers in the array satisfies the pattern's conditions. The overall approach leverages the stack to efficiently manage potential 3 values while dynamically updating the 2 candidate, ensuring that the solution runs in linear time. This implementation is both time and space efficient, making it well suited for handling large input arrays. To solve this problem, we start by checking if the array has fewer than 3 elements, as a valid 132 pattern cannot exist in such cases. Here, the array is 1, 2, 3, 4, which has 4 elements, so we proceed. We initialize an empty stack and set the variable third to -infinity. The idea is to traverse the array in reverse order and maintain third as the second largest number in the 132 pattern. Starting with the largest number, 4, we check if it is less than third. Since third is -infinity, this comparison is false. Then, we check if there are any smaller elements in the stack. As the stack is empty, we simply push 4 onto the stack. We repeat this process for the next number, 3. Again, since 3 is not less than third and no smaller elements exist in the stack, we push 3 onto the stack. Similarly, for the numbers 2 and 1, the same checks hold, and both get added to the stack. At the end of this traversal, the stack contains 4, 3, 2, 1, but number 132 pattern is found. After completing the traversal of the first example, we confirm that there is no valid 132 pattern in the array 1, 2, 3, 4, so we return false. Now, let's look at another example, nums equals 3, 1, 4, 2. We again begin by checking the array length, which is sufficient, so we proceed. As before, we initialize an empty stack and set third to -infinity. Starting the reverse traversal with the number 2, we find that it is not less than third, and since the stack is empty, we push 2 onto the stack. When we encounter the next number, 4, it is still not less than third, but this time we have an element in the stack, and we pop it because it is smaller than 4. This updates third to 2. After updating, we push 4 onto the stack. Then, we move to the number 1. Here, we find that 1 is less than third, which means we've identified a valid 132 pattern. Specifically, the pattern is 1, 4, 2. At this point, we can stop and return true since we've found a solution. Now, let's examine a third example with nums equals -1, 3, 2, 0. As always, we start by checking the array length, which is sufficient, and proceed by initializing an empty stack and setting third to -infinity. During the reverse traversal, we first encounter the number 0. Since it is not less than third and the stack is empty, we push 0 onto the stack. Next, we look at the number 2. Again, it is not less than third, but we pop elements from the stack that are smaller than 2. Here, we pop 0, updating third to 0, and then push 2 onto the stack. Moving on to the number 3, we find it is not less than third, and since no smaller elements in the stack exist, we push 3 onto the stack. Finally, we examine -1, which is also not less than third. Without any further changes, we add -1 to the stack. At the end of this traversal, the stack contains 3, 2, -1. Despite traversing all elements in the array, we did not find any instance where a number was less than third, meaning no valid 132 pattern exists in this example. Therefore, we return false. This example demonstrates how the algorithm handles cases with negative numbers, showing that the logic applies consistently regardless of the specific values in the array. The time complexity of the solution is O, n, where n represents the length of the input array nums. Let's break this down step by step. First, the algorithm performs a reverse iteration over the array. Since it visits each element exactly once, this takes O, n, time. Next, we consider the stack operations. Each element is pushed onto the stack only once, and at most, it is popped once. This means the total number of stack operations, including both pushes and pops, is also O, n. When elements are popped, it happens within the while loop, but each element can only be popped once, so the total pops are still bounded by n. Finally, we have constant time comparison operations during each iteration, such as checking if the current number is less than third or if conditions for the while loop are satisfied. These checks are O(1) per iteration, which adds up to O(n) overall for the entire array. When we sum up all these components, reverse iteration, stack operations, and comparisons, the overall time complexity remains O(n). Now let's analyze the best, average, and worst cases for this algorithm. In the best case, the array does not contain a valid 132 pattern. For example, if the array is sorted in descending order, no stack pops are necessary, and the algorithm simply pushes all elements onto the stack. Even in this scenario, the time complexity is O(n). In the average case, the algorithm performs a combination of stack pushes and pops while processing the array, but the total operations still remain linear, resulting in O(n) complexity. In the worst case, every element is both pushed and popped, such as in an ascending array, but even then, the total number of operations does not exceed O(n). Shifting to space complexity, the solution requires O(n) additional space. This is primarily due to the stack, which in the worst case could grow to the size of the array. Additionally, the variable third, used to track the middle value of the 132 pattern, only requires O(1) space. Therefore, the total space complexity is O(n). To summarize the space complexity breakdown, the stack requires O(n) space, as it may grow to the size of the array in the worst case. The auxiliary variable third only adds O(1) space. When we combine these, the total space complexity is O(n) plus O(1), which simplifies to O(n). To understand the efficiency of this solution, let's compare it to a brute force approach. A naive method would involve iterating through all possible triplets, nums, I, nums, j, nums, k, for indices I less than j less than k to check for a 132 pattern. This requires 3 nested loops, resulting in a time complexity of O(n) cubed. However, the brute force approach does not use additional data structures, so its space complexity is O(1). In contrast, the optimized approach we've implemented reduces the time complexity to O(n) by utilizing a stack and processing the array in a single pass. While it requires O(n) space for the stack, the dramatic improvement in runtime efficiency makes this trade-off worthwhile. Finally, here's a mathematical proof to confirm the time complexity of O(n). The key insight is that each operation is directly proportional to the size of the input array. First, every element is pushed onto the stack at most once, which means there are n pushes. Similarly, each element is popped from the stack at most once, leading to n pops. The while condition, which governs stack pops, is checked during each pop operation, so this contributes to at most n comparisons. When we combine these components, n pushes, n pops, and n comparisons, the total number of operations is clearly linear with respect to the size of the input array. Hence, the time complexity is O(n). One of the most common mistakes when tackling the 132 pattern problem is relying on brute force without optimization. This approach involves iterating over all possible triplets of indices, I, j, k, and checking for the pattern directly. While this may seem straightforward, it has a time complexity of O(n) cubed, which quickly becomes impractical for large inputs and can lead to time limit exceeded errors in competitive programming. Another frequent error is misunderstanding the order of indices. For the pattern to hold, I must be less than j, and j must be less than k, but some solutions mistakenly use the wrong order or check conditions like I, a, j, a, k, which don't align with the problem's definition. Mismanaging duplicates or edge cases is another pitfall. For example, arrays with fewer than 3 elements or arrays with repeated values like 1, 1, 1, 1 can lead to incorrect assumptions if not handled carefully. Lastly, when using stack-based approaches, improper management of the stack is a common issue. The stack must be maintained in decreasing order to track potential k elements, and failing to do so can result in missed patterns or incorrect results. Another crucial aspect to consider is space complexity. While optimized solutions often provide significant improvements in time efficiency, they may require additional data structures like stacks or arrays. Ignoring the space complexity of these solutions can lead to suboptimal implementations, especially when working with large inputs. Now, when it comes to interview scenarios, one of the most efficient approaches to solve this problem involves using a stack to track candidates for the k value while iterating over the array in reverse. This approach brings the time complexity down to n. The key observation here is that the 132 pattern has a strict ordering, where a I must be less than a k, which in turn must be less than a j. By maintaining a stack of potential k values, we ensure efficient comparisons and avoid unnecessary computations. During interviews, it's important to not only explain why this solution is optimal but also discuss the trade-offs compared to other methods, such as brute force. Interviewers may also probe into why iterating backward is necessary for the stack-based approach. Finally, make sure to test edge cases thoroughly. Examples include arrays with fewer than 3 elements, strictly increasing or decreasing arrays, and arrays with duplicate values. These tests ensure your solution is robust and handles all scenarios correctly. This problem shares similarities with several other algorithmic challenges, especially those involving stack-based approaches. For instance, problem 84, largest rectangle in histogram, utilizes a stack to efficiently solve a geometric problem, while problem 739, daily temperatures, employs a monotonic stack to calculate the nearest greater temperature for each day. Similarly, problem 496, next greater element I, uses a stack to find the nearest greater lookup for elements in an array. Understanding these related problems can deepen your grasp of stack-based techniques and their versatility. Now, when comparing different approaches to the 132 pattern problem, brute force is the most straightforward but also the least efficient. It involves checking all possible triplets I, j, k, and has a time complexity of n cubed, making it impractical for larger inputs. The optimized stack-based approach, on the other hand, reduces the time complexity to n by maintaining a monotonic stack to track potential k values. However, this method does require additional space for the stack. An alternative is to use a binary search with a sorted data structure, such as a balanced binary search tree or a sorted array, to track a j while iterating through the array. This offers a time complexity of n log n, but demands careful implementation and additional space for the data structure. Each method has its trade-offs, and understanding these can help you choose the best approach depending on the constraints and requirements of the problem. Great job following along. To wrap up, we reviewed the 132 pattern problem, key algorithms, and takeaways for solving similar challenges. Keep practicing, and stay curious. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!